Hello friends, in our last video we saw how to multiply matrices and what are the necessary conditions required for the same. And if you recollect, we ended the last video with an interesting question, which is if there are two matrices A and B, is the product AB equal to the product BA if both of them are defined? Well, it's very obvious if A and B are real numbers, since we know that the commutative property holds in real numbers. Now, what about matrices? Let's test this with help of some examples. So, here are matrices A and B of the same order. And now, we know that the product AB is defined. So first, let's find the product AB. So if we calculate, the product AB will be 20, 25, 36 and 45. Now let's find the matrix BA. Observe that even the matrix BA is defined as well. So the matrix BA will be 28, 37, 28, 37. Now tell me whether the matrix AB is equal to the matrix BA or not. So we can clearly see that the elements of the matrix AB are not equal to the corresponding elements of the matrix BA, which implies that these two matrices are not equal. So what can we conclude from this example? We can conclude that the commutative property does not necessarily hold in multiplication of matrices. But there are some matrices in which the commutative property will hold. For example, consider these two matrices C and D. First, calculate the product CD and then calculate the product DC. From here, you can clearly see that the product CD is equal to the product DC. So in this case, the commutative property will hold. So from these two examples, we can conclude that the commutative property does not hold necessarily in the multiplication of matrices. This is one of the ways in which the matrices are very much different from the real numbers. So we can conclude that the multiplication of matrices is not always commutative. Now, by more examples and trying out the different combinations of the products, we can conclude that if there are three matrices A, B and C, the product of the matrix AB with C will always be equal to the product of the matrix A with the matrix BC. That is, the associative property holds in the multiplication of matrices. So you take three matrices in the same order and first multiply the first two matrices and then multiply the third matrix with the product obtained, or you multiply the last two matrices first and then multiply the first matrix with the product obtained. The resultant will be same in both the cases. So the associative property holds for the multiplication of matrices. So we saw that the commutative property does not hold necessarily in multiplication of matrices, and the associative property will hold in the case of multiplication of matrices. Friends, now if you have three matrices A, B and C, and if you want to find A multiplied by B plus C, then we will first add the matrices B and C and then we multiply the matrix A to the sum B plus C. That is how we get the matrix A multiplied by B plus C. Now on the other hand, if we find A multiplied by B and A multiplied by C, and then if we add those products, then we get the matrix AB plus AC. Now we can clearly observe that both these matrices are equal. So, from this example, we can conclude that matrix multiplication is distributive over addition. That is, if there are three matrices x, y and z, then x multiplied by y plus z will be equal to x multiplied by y plus x multiplied by z. Also, the same thing applies even for the subtraction as well. That is, matrix multiplication is distributive over subtraction as well. That is, x into y minus z will be equal to x into y minus x into z. While applying these properties, remember that the order of the matrices y and z must be same, since they are being added and subtracted. Also, the multiplications xy and xz must be defined. And now, here is an interesting question for you guys. What role does the number 1 play in multiplication of numbers? It's very simple, right? You take any number, you multiply it to 1, you get the same number as the resultant. So, the number 1 is acting as a multiplicative identity in the multiplication of numbers. That is, you take a number, you multiply that number to 1, then you get the same number as the resultant. And for this reason, we call the number 1 as the multiplicative identity for the numbers. And now, in matrices, there is a matrix which is just like 1 in the case of numbers. What is that matrix? Yes, it's the identity matrix. We already learned about the identity matrix in our previous videos. So, identity matrix is a square matrix in which all the principal diagonal elements are equal to 1 and rest of the all elements are equal to 0. So, you take any matrix, multiply it with the identity matrix, and then you will get the same matrix as the resultant of this product. But remember that this product must be possible. Now, here the order of the multiplication is not important. You take matrix and then you multiply it with the identity matrix, or first you take the identity matrix and then multiply with the matrix. In both of these cases, the product will be the same. Finally, we can conclude that the product of an identity matrix with any matrix, or the product of any matrix with the identity matrix, is always equal to the matrix itself if that product is defined. Friends, here is a matrix A of the order 2 by 2. And now, if you want to find the matrix A squared, how will we do it? Sometimes, generally, we tend to square each element of the matrix A, which is very much likely to happen here. But remember that square of anything means that we have to multiply that by itself. For example, what is 2 squared? It is 2 multiplied by 2. Similarly, A squared will be the matrix A multiplied by itself. So, A squared will be A multiplied by A, which is nothing but 11, 16, 40 and 59. Observe that here A is a square matrix, and we can find square of any matrix if and only if that matrix is a square matrix. For example, if X is a rectangular matrix, then we cannot find X squared, since the number of columns of X will not be equal to the number of rows of X, and this product will not be feasible. So, the matrix A squared is A multiplied by A. Now, for any square matrix A power n, where n is positive integer, will be equal to A multiplied to itself n number of times. Again, remember that the matrix A must be a square matrix. If matrix A is a rectangular matrix, then a power n will never be feasible. And now here is another interesting question for you. Let's say X is a matrix of the order n by n. Now what will be X raised to the power 0? To answer this question, first let's answer this one. What is 6 raised to the power 0? It's 1, right? We know that any real number except 0 raised to the power of 0 is always 1. And 1 is the multiplicative identity in case of the numbers. And now coming back to our original question, what would be the answer now? So we have to look for the multiplicative identity in matrices. And we know that it is the identity matrix. So X raised to the power 0 will be the identity matrix of the same order as the matrix X. So any matrix raised to the power of 0 is always equal to the identity matrix of the same order. So friends, that's all for today. I hope you understood the properties of multiplication of matrices. In our next video, we'll do some problems related to these properties of multiplication of matrices. As of now, let's summarize what we have learned so far. The multiplication of matrices is not necessarily commutative. Associative property holds in the case of multiplication of matrices. Matrix multiplication is distributive over addition and subtraction. Identity matrix acts as the multiplicative identity in the multiplication of matrices. For any square matrix A and for any n being positive integer, a power n is nothing but a multiplied to itself n number of times. For any square matrix A raised to the power 0 is always equal to the identity matrix of the same order.